Okay, so the water is down, so we can talk about the ice. Ice we will mention relatively brief. Our textbook has like 5 pages talk about that's very wordy. So we want to talk about ice structure. Just do some of the easy understanding. Okay, ice. This is we say is one water compact by 4 molecules of water. In we say it's a cubic tetrahedral structure with halos. We know that the density of ice is 0.9 gram per ml. Okay, it's a little bit lower than the water. So that's why you can see the water is floating on the ice is floating on the ice, and we also call this the hexagonal structure. So what it looks like, if you are cutting the ice, it's a hexagonal structure. Looks like that. So we have O oxygen right here, and then we had a so-called H is right here. Then go here, then go here, go here. We have one here, one here, 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 and then one here. So this gives you some of the structure we can talk about is if there is n molecular of water, how many possibility of H atoms arranged? And ideally, there should be 4 times the power of n. But when you see here, there is a restriction. So the electron could be go this way, or the electron could be go connected with this way. Which means there is a restriction is 1 oxygen has to be coupled with 2 hydrogen atoms. So the arrangement is 3 divided by 2 times the power of n. Okay, it's just a mess. We just go over it quickly. It's a mess. We don't want to go much detail about that. Number 3, we want to very briefly mention when you add a salt, okay, they will be decrease the melting points. This is especially last week. We know about that. They spray the salts in a very freezing day to let the snow and the ice crystal get dissolved. There is a true theory about that. One theory they talk about that is these water molecules compact with ice crystal. And once you add a sodium there, the sodium chloride solution is like a scissor. Is they slice these chemical bonds and let them be dissolved. So the ones talk about is scissors. I call it a scissor theory. I think it's very briefly understand. It's like a scissor. The second theory they call it a purity theory. The purity theory means if in the crystal ice, it's like purity, which means they do not like any of the foreigners, and the sodium and the chloride is a foreigner, so they will repel. They try to repelling it, and once they repel these out, the ice crystal, they will be accumulated to group them. They like say group these because they want to repel these things. When they grouped there, become a purity area. In these intersections, they will generate superchlorine water. And the superchlorine water is usually much less than 0 degrees Celsius. And then the superchlorine water and the ice are coexisting. And once they coexisting, they start to do the melting process. So that's a purity theory. Okay, just to very briefly talk about the salt will decrease the melting points. From the food chemistry standpoint, we talk about food preservation. We want to talk about the impact of the ice for the water quality. So that's we talk about impact of ice for food quality. So when we talk about this, we need to understand the first very simple concept: 0 degrees Celsius. We just using 0 degrees Celsius as an example. Okay, 0 degrees Celsius is water solidified, become ice. This is number one. Number two, 0 degrees Celsius is ice melting to become water. This is everybody knows. However, the last one is important. At 0 degrees Celsius, ice and water coexisting. This is important, or co-present. Okay, so that's the first thing. The second thing, we want to talk about is water. So we know the temperature impact water evaporation or condensation. So we mentioned about last class, in this closed chamber, we have a water molecule here. We have a water molecule here. If the temperature is increased, the water will be flee away. They'll vibrate dramatically. And they'll vibrate, which means the evaporation will be dramatically decreased with decreasing temperature. And later what happens? If it's decreased from 20 to close to, let's say, 1 degree Celsius, the water molecule will happen is sluggish. This is the same thing, like in a cold weather. You have only a t-shirt there, then you go outside, you're feeling like sluggish, like this. So when they sluggish, what happens? The water molecule, they will be compact or stacked together, become an embryo. This embryo will cause nucleation. Okay, that's some background information you need to know. The temperature is decreased. They start to sluggish, they stack together, have an embryo. Once the temperature goes to 0 degrees Celsius, they will start to have nucleation happens. Now, regarding nucleation, there is two different types of the nucleation, which is homogeneous and heterogeneous. Heterogeneous is more complicated, but we can give you some example later, and homogeneous is easily to understand, so we want to talk about that. So what happened? There is a curve, talks about. And the curve is interesting, looks like this. Not very good. This is not that one. It's flat. Flat like this. X-axis, crystal size. You can say nanometer. Y-axis, temperature. What's the temperature range? 0 degrees Celsius, minus 10, minus 20, minus 30. That's degrees Celsius. So what happened? If it's at 0 degrees Celsius, the nucleation will happen. But what's the problem? The ice crystal is a large size. Could be as large as 120 nanometer. Okay, when the temperature decreased, if it's decreased to minus 30 degrees Celsius, the nucleation is also happening. But the ice crystal is much smaller. It is only 20 to 40 nanometer. Once the temperature is started to decreasing more, at minus 40 degrees Celsius, that happened is 100% homogeneous nucleation. Then no ice crystal, ideally. Which means at minus 40 degrees Celsius, we get free water. Why this is important? We don't like the ice crystal large. Large ice crystal damage the tissue of food products. So I gave you a very simple example. You have a beef. You vacuum package, then you put at our home refrigerator. That is a minus 10 or 5 degrees Celsius. Then you put it there. It starts to decrease to go 0 degrees Celsius, then go down. The ice crystal is larger, 120 nanometer or above it, depends on different products. That's all the crystal large. It will damage the tissue. So how you find it? 3 months later, when you take out of the beef, when you saw it, you see a much drip comes out. And also you will see the tissue is damaged. When you're cooking that beef, it's no longer a beef. You don't like that one at all. So what this tells us? You have to do a rapid cooling. It is important because this comes out another curve. Freezing point this curve, crystallization, and above curve, nucleation. What we want, more number of nucleus less number of ice crystal. If we have a less number of nucleus, what happened? Large number and large size of crystal. But we don't like it. That's why we have to do a rapid cooling. So how we do the rapid cooling in the food industry? Liquid nitrogen. Is that right? Liquid nitrogen. If I have, let's say, a chicken fillet, liquid nitrogen, we put it there. What happened? The temperature is very low, go minus 192 degrees Celsius. The water looks like it's boring, it's gone. So liquid nitrogen can do that because it's completely reduce the temperature below minus 40 degrees Celsius. What happens is 100% homogeneous nucleation. So liquid nitrogen can do a lot of the rapid cooling for so-called organized thin dimensional products. What are these? Example, chicken fillet, fish, salmon fillet. That we can do that. Okay, what are the other one to do? The other methods is seeding. Seeding gives you heterogeneous nucleation. What is the examples? Because the idea is we put more seeds there, more nucleus there. They can start to do nucleation instead of do crystallization. A very easy example is our lab we do, but you never notice it. How we preserve bacteria culture. What we do? We add glycerol. And ideally we add sodium triphosphate. We don't do that one often. What does glycerol mean? Cryogenic protectants. When you glycerol, you added your seeding. You add the seeds there. Let the nucleation happen. So the crystal will not damage the cell culture of the bacteria. Obviously, this has to be in a low temperature. So at least minus 20 degrees Celsius or minus 80 degrees Celsius. Okay, because we don't want a 0 degrees Celsius, the crystal size is huge. Other examples, we have crystallized, we call it modified fatty leathers, like this. This is in margarine, is that right? Margarine. We make it in the margarine products. We'll mention margarine and shortening all the time when we talk about the lipid section. And we also could add is ground lactose crystal. This is we do evaporated milk heat exchange. Is that right? Heat exchanger. So we just gave you some of the examples to understand the ice, what it looks like. Okay? So, you textbooks, they mention about plastics, there's a glass status. We'll just skip that. It's too complicated about that. Last thing we didn't mention, you talk about water activity, you talk about pH. Because this is the food microbiology, so I don't want to talk about that. Low acid foods, remember we talked about this in the other classes. That's water activity, more than 0.85, pH, I always say approximately 4.6, like canned foods. Okay, this is low acid foods. And in the West Virginia, Susie Slider set up a standard is pH less than 4.0, that's all. And it's creates to prevent the endospore forming. But this is for the microbiology, so it's in the textbook, but I didn't mention that too much, okay? So, we talk about sorption, isotherm, desorption, we talk briefly about the ice, and then we left two things I have mentioned is a phase diagram of the water, and we're going to talk about chlorine water, and there's we also talk about the electrolyzed water, ozonated water next week Tuesday. Then we're going to go back to look at the slides. There's something we didn't mention, we use the slides. Then we conclude the first section of the water. Okay? Then we move to second one is the protein and amino acids. Okay? So that's all we have today.